Okay, let's continue. The next topic we are going to be looking at is 2.3 and 2.4, and this is going to officially signal the beginning of calculus, where we're going to talk about the concept of a limit and continuity. But, I was thinking before. All right, before we begin that 2.3, 2.3, I want to talk about, I don't know if I want to phrase things in the affirmative or the negative. Things. So, to go back to the topic of common mistakes, and whether or not I should write them in red.
Write them in blue.
Blue for common mistakes, because it's sad. You don't want to make this and be sad. And I write green for go, you got it, yeah! Okay, all that. Common mistakes. Now, these aren't math mistakes necessarily, but they can affect your math and a lot of other things you're doing. So, a lot of times when people get a bad result on a test, of course, it's not fun, it's not nice, it's not fun for anyone. I don't like giving bad grades any more than anyone likes getting them, but you do not, it's gonna sound really cheesy, but don't give up. I don't really know another way to say it. It really sounds cheesy, but it's actually very practical. There are a lot of times where students prematurely give up on something, and I see some students, they'll give up and they'll withdraw from a class, which sometimes I think it's too early. Other students will actually stay in the class, but mentally they kind of resign themselves to their fate. They're kind of going through the motions, and they kind of decide, well, you know, things aren't going so well, I know the class is going to end up, and they just stick around, but they don't really have the intention of doing well. You do not want to end up in that position. And it's not because of, oh, the universe is going to help you believe, or any foolishness like that. One of the real reasons why this is a thing in practical terms is because as humans, we build habits. Now it turns out giving up can become a habit. When things get kind of rough, you just don't want to deal with it, right? You know that all those times when people are like, well, I kind of know what I should be doing, but I don't do it, and they might attribute this to all sorts of personal flaws and all. It's habit, right? They don't do what they're supposed to do because they're in the habit of not doing what they're supposed to do, and it's that simple. Okay? If you start to, when things start to get rough, you start saying, maybe it's just not going to happen, right? That kind of thought, you do it often enough, it becomes a habit to the point where even when you decide that, hey, I should really do something, you're not going to have enough fire or power behind that thing, right? And so you're going to be like, okay, I'm going to study. But you're not going to study as long as you should. You're not going to study as hard as you should. Because somewhere in the back of your mind, you're giving up. You need to really fight against that feeling of despair. You have to understand that you are not constant, right? As a human being, you can adapt, you can become better. It's kind of what human beings are. It's kind of why we're the dominant species. We can adapt, right? It's kind of your best trait, right? 90% of the species on this planet has died. We're here on top of the world. Why? We could adapt, right? Weather like this would kill us. We invented codes. What other animal can do that, right? Adapting is a part of your strong suit, but if you tell yourself it's not, and you start having thoughts like this, what happens is you're going to ingrain a certain habit where it's just going to be a self-fulfilling prophecy. That's why people who don't do well in math in the past, they kind of think of themselves now as, I'm a person who's bad at math. And it just grinds through their entire life. And then they pass it on to their children, and now their children fear math, and then, you know, there's a cycle that's continuing. You have to break that cycle, right? And it comes down to just not giving up, deciding that, hey, Things are bad now, but I have the potential to be better. And you should be aware that no one wants to fail you, right? Myself, the administration, the people in the math department, the people in the SAC Center, they want you to succeed. We all want you to succeed. No one wants to be the guys that just fail everybody. That's actually not a good business model. For everyone to come just fucking, let's just beat them down and just like destroy their confidence and then just chuck them out. That's never the goal. And I feel like a lot of times people feel that way, like, Jhevon probably loved giving me this script. He just wanted to look at this large X that he wrote. I wrote that because I want to get your attention, not because I want to push something into your face, okay? No one here wants you to fail. We're all very interested in your success. But one of the main things that are going to stop you from that success is your own mind, actually. That's going to be your biggest enemy. Bigger than, even if you had a professor who wanted you to fail, he is not going to be as big an enemy to you as your own mindset that's telling you to give up. You have to understand that you can adapt. Sometimes there will come times, forks in the road, where you kind of have to make a decision and to say, like, you know what, this course of action, I should quit this course of action and try something else. These times happen, but most people usually do not ever, they give up way before that point, way too prematurely. And at that point, when you have to make such a decision, it shouldn't be an emotional one. It shouldn't be like, oh man, I got a bad grade, this quiz sucks. And out of that emotional despair, you make a decision. You shouldn't make decisions like that. It should be a practical one. It should be like, okay, in order to improve to a grade I want, I'll need to be able to study 2 hours a day. I only have 1 hour a day. It is a practical decision to say, you know what, I'm going to drop the class and take it another semester. That's a different kind of decision, right? That one is about really examining the pieces that are in play and actually making an informed decision about it. You don't want to make a decision from despair or sunken emotions or sunken feelings, because then that just becomes a habit. That just becomes how you do things, and then you start to do things just because you feel like it. So you should go to the gym today, I don't really feel like it. But you know what? Because you're so used to making decisions that way, that will be the easier thing to do. Right? And a lot of the people that we sort of look up to, and you'll think that, oh, they have so much discipline. They don't really, right? A lot of people wake up and don't feel like going to the gym, but they still go anyway, right? It's not a decision that is an emotional one for them. You just think that, oh, they love being there every day. No, some people just go because they know that's what they should do. And they have a goal, and they just said, oh, I want to run a marathon, I need to run a certain amount of days in order to be able to do that. So they look at the goal, they don't look at where they are, they're like, man, I ran 1 mile yesterday and almost died. They look down the road and say, I want to be able to run a marathon in 3 months. I might suck today, that doesn't matter. In 3 months, amazing things can happen, right? And when you take that mindset, that's going to power you through, as opposed to just giving up in the beginning after 1 bad run. Okay, maybe I'm just not cut out to be a runner. That's not how it works, right? What you need to do, and what I tried to outline last time, was a strategy for you to really look at the situation by the numbers and just be like, okay, here's a skill assessment, here's a concept assessment, here's this, here's that. You have all this information at your disposal, and you make decisions based on that, right? So don't give up, really try to, again, ask for help, not go fun, the redo. Ask for help, apply strategies, do something, right? You need to do something. I can't guarantee that you would always emerge victorious, but I can kind of guarantee, like, statistically speaking, you'll emerge victorious most of the time, right? Once you have that mindset that, you know what, I'm just going to keep improving, keep improving, keep improving. Really pay attention. You really want to look at yourself. You don't want to have that kind of victim mentality. Oh, these people are just going to give me a bag. I'm never going to be able to be one of Jhevon's tests, blah, 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 blah. This kind of victim mentality. No. Look at my test. dissect it. You're going to go over it 3 times. And then you should, after you actually go through and do what I'm saying, then you can start to actually look for patterns. Like, okay, so did these questions look like the review problems that he asked us about? They did. And okay, but all right, so he gave us a bunch of review problems, and he picked these specifically. Why would he do that? And if you figure that out, what kind of problems would he pick from the next review to put on it? Right? What would be important? Right? You really want to think about dissecting the situation as opposed to being drowning in your own emotions and then trying to give up. Okay? And as I said, a lot of times it just comes down to paying attention. That will actually solve a lot of your issues. Right? Not only pay attention to what I'm doing or what's going on, but paying attention to yourself, kind of knowing your weaknesses, how you would react to certain things, how you actually think about certain things. And sometimes you have to kind of look at it with some sort of emotional detachment. So one thing would be to, now nothing can ever really be truly objective, but you do want to talk about trusting objective assessments. Right? So even when I'm grading, I kind of grade it in such a way that I don't want biases to show up. So I don't even look at the name of the person of the paper that I'm grading, and I'll usually grade all the questions all at once so that I kind of grade them fairly and so on and so forth. So you should be aware that that grade you're looking at is pretty objective, okay? Now, what you don't want to do is to throw that away, right? That's, a lot of people do that. It's the wrong thing to do. A lot of people might say things like, you know what, I really understand more than this. I just don't think Jhevon properly assessed me because I feel like I understand more than this grade. That's you ignoring this. Think of that number on that paper as the true measure of where you currently are. Now, once you accept that fate, because it might be painful, don't give up. Immediately put into a strategy of saying, okay, here's where I am, there's where I want to be, let's figure out what's going to take to get from here to there and put a plan in action. Make sure that, logistically speaking, this can be put in action, right? Because you also have people with the other thing. They really try to do everything, but they really just, you don't have the time, right? Taking 5 classes, you're a single parent working full time. Probably you want to cut something, right? That's not an emotional decision. That's a practical decision. But most people I don't think are in that boat, at least in this class. And so it just comes down to, okay, here's where I am. It really sucks where I am right now, but let's accept it and let's move on. Let's not think to myself, you know what, I'm really 20 points better than this, so I'm going to prepare as if I'm 20 points better than this, right? Because that matters, right? The kind of things a student who gets a grade of 40 does is different from what the kind of things a student who gets a grade of 60 would do. These would require 2 very different things. If you're thinking of yourself as a 60 when you're really a 40, you're just introducing ways for you to fail at that point, because you're not going to put in an effective plan. Accept where you are now and be like, okay, this is what we're working with. You know what? I got 2 months to get to here. Let me go do all the recon, get professional help and response on what I've discovered about myself, come up with a plan, and just do it, right? We're not going to give up. You just understand that, hey, I'm a human being. Adapting is kind of my thing, right? It's kind of what we do. That's why a lot of things we have to worry about. A lot of times adapting, you can't even become the enemy. Well, that's a different scenario, right? So if you do start, again, to go with the gym example, if you do start to become that person who goes to the gym every day, you'll realize after a while, doing the same thing is not challenging anymore. And so you always have to kind of push the boundaries, right? It's because your body adapts. You adapt more than you realize. But you need to give yourself that permission. Because otherwise, what you're doing is you're adapting to giving up. That's not what you want to do. You do not want to adapt to the giving up mindset. A lot of people adapt to that, and that's why they never get any better. That's why they can be bad at math for their entire lives. It's not something you have to be bad at. Do not accept that as a given. That being said, let's actually move on. Just really start taking things seriously, start paying attention, put a plan into action, put in the time, right? And as I was saying about habits, the more you do it, the easier it becomes, right? So, yeah, the first time you do what I just asked you to do, it's gonna suck. I'm gonna tell you right now. Go through the same thing 3 times over, spending the time to actually go through it without looking at the solutions, spending the time to go talk to a tutor. It's gonna suck, it's gonna take a lot of time. But you know what? Once you do that enough, it'll become a habit. Your body will literally adapt to doing that. Right? Your brain will adapt to doing it. You realize that by the second run through of your test, you can do it twice as fast. You'll start to make up time, right? And ultimately, if you do these assessments properly, it saves you time in the sense that if you really prepare properly, you'll never end up in the situation where you get a bad grade that you have to recover from. So actually, by putting in the time before, you actually save more time afterwards. So the time investment is worth it, right? Find the time. Do what I asked you to do. Make the time. If there is literally a very practical, pragmatic reason why you cannot find the time, then that's a different scenario. And that you would have to talk about. That you can come to me and ask for my advice. Okay, here's where I am, here's what I'm thinking we'll need, and I'm not sure I actually have the time to do all this. Then you might be able to try something, and if not, maybe you drop the class and come back, maybe you do something else. But don't actually give up. You need to actually decide that I'm going to find a solution to this problem of getting bad grades. And I need to figure out what that solution is, and you need to be confident that you can actually pull it off, because you can. And that I'm sure about. You can. Believe it or not, I myself wasn't good at math. I know a lot of people say this, and no one ever believes anyone when they say something like that. You know, I never used to all be, yeah, right, whatever. You were probably born knowing about this. Yeah, no. When I was younger, where I went to school, there came a point where you had to choose like a path, like you had to choose that, oh, I want to go down the business path, or I want to go down the science path, or I wanted to go down this path. And I wanted to do science, but they actually stopped me because my math sucked. Right? So I came back from that disappointment, and I'm a math teacher of all things, right? Literally the thing that stopped me from making a life decision was that I sucked at math, and here I am teaching, right? Because I actually decided, you know what? Yeah, I suck at math now. I don't want to do that anymore. Here's a plan that I'm going to put in. And unfortunately, the plan worked so well that I started liking math after that. I'm like, you know what, math is pretty cool. Maybe I should major in that when I go to college. That's where it went. Went from, oh my God, I really suck at this stuff. You know what, this is pretty cool. I think I can actually do this for a career. Right? You'll be surprised. You'll never know what you're capable of if you just give up. You're just like, oh, this is kind of uncomfortable. This is kind of hard. Maybe I'm just not cut out for this. I mean, to be clear, there are things that people aren't cut out for. It's just that a lot of people make that determination way too early. Like most people just, they never actually give it a fair shot. Do not let that be you. So we're going to do, and I like to do these 2 sections in one. So we're going to cover everything in these 2 sections. But I think it flows nicer if you just think of them as one thing as opposed to 2 separate things. So we're actually going to talk about 2 sections in your book, 2.3 and 2.4. This is where we're talking about limits and continuity. There are a lot of overlapping ideas here. I just think it's better to do them in one. First, some remarks. we look at calculus, which is what we're going to start now. It turns out calculus is a combination of two branches of mathematics that we have actually known how to deal with for a long time. So calculus has been studied for centuries, even millennia. I think Archimedes knew some calculus even. But they were kind of fragmented sections of mathematics. People were doing parts of calculus, but there was no unifying theory of calculus as we know it today. A unifying theory for calculus came in the 1700s with Isaac Newton and Gottfried Leibniz, which is why those guys are usually thought of as the inventors of calculus, but they're not actually. They just kind of put it all together in one little neat package, and they found a common thread. But calculus really studies two main things. There are two branches of calculus. There's called differential calculus. Right? The main tool in differential calculus, the main object that we use to solve problems in this branch of math is called the derivative. Right? When you say you're going to use the derivative to solve a problem, you call it differentiation, and therefore we call it differential calculus. Okay? Now, the goal of differential calculus was to solve something that we call the rate problem. So this was a problem that early mankind wanted to know how to solve. Figuring out the rates at which things are moving, right? Because things change, right? Sun rises, sun sets, seasons come and go, the tide comes in, the tide goes out. Change is constantly happening. And a lot of times knowing how fast these changes were happening would put you in a position of power to make predictions, to make plans for the future, because we know, okay, in 3 hours this is going to happen, so we need to get this done before then, right? That sort of idea, to figure out how fast things are moving. So we wanted to figure out the so-called, and there are many ways in which this problem could be stated, but it is, the blanket statement for this would be the rate problem. We need to figure out how fast things are changing, right? And the answer to the rate problem was something that we call the derivative, which we will derive. We'll derive the derivative. And the branch of math that studies the derivative and its applications is called differential calculus. This is one half of calculus. Another half of calculus is called integral calculus. Right? So the main tool in integral calculus is called the integral. The integral. Now, the goal of integral calculus is actually a very different goal. The goal of the integral calculus was to solve what we call the area problem. In other words, we need to figure out how much space something takes up, right? So the study of math that studies how to calculate how much space something takes up, this is saying that we want to solve an area problem. The integral is a pretty useful tool for that endeavor. So you can imagine, especially even in early commerce, let's say you have a plot of land and the government is charging you property taxes based on how much land you have, and they're charging you based on how many acres you have, and you're like, how do you know how many acres I have? My land has this really irregular shape. How do I know you're not overcharging me taxes? How much space does my land actually take up, right? If something is a rectangle, yeah, we know how much space it takes up. But what if something has a weird shape around the edges? Then the problem becomes a little bit more complicated, right? So you want to know, if you were that farmer with a plot of land, is the government overcharging you for taxes? Maybe they're undercharging you, you don't want to say anything. But figuring out how much space something takes up, that is the goal of integral calculus. Now, curiously enough, people have been studying these different things separately for a long time. But it turns out, oddly enough, that these two things are connected. Figuring out speed and area are actually inextricably linked. They're like two sides of the same coin. And these were found with what we called the fundamental theorem of calculus. And this was what was proven in the time of Newton. So there's a theorem of calculus. It connects these two branches of mathematics. right? So you have people over here trying to figure out how fast something's moving. People over here trying to figure out how much space something takes up. And then Newton and his professor comes on and say, you know what? You guys are really studying the same problem and don't even realize it. You're coming from it from different angles, okay? Which is very strange that speed and area would somehow have a relationship, but it does. And the appreciation of that relationship is calculus. That's what we're studying. So the study of calculus is the study of derivatives, integrals, and their applications. Now, in Math 2009 specifically, we will not be touching any integral calculus. So this is not in Math 2009. So this entire here and here, we don't particularly care about, right? So in this course, we're going to talk about this guy. We're going to talk a little bit about the derivative, what it is, and problems we can solve with it. We're going to look at applications of the derivative, okay? In the next course, the follow-up to this, you'll actually start talking about this side, and you'll also talk about the connection between the two. But for us, we're going to spend a little bit of time on this guy. So this is going to be the next third of the class. So 1/3 of the class was pre-calc, 1/3 of the class is going to be differential calculus, and 1/3 is going to be us deal with matrices. Okay? So for now, we are going to stick with differential calculus for a while. And it turns out that they do have another connection. So if we wanted to talk about what is calculus, you can say calculus is the study of derivatives, integrals, and their applications. It's figuring out how fast things move, how much space they take up, and how we can apply this to solving problems. But it turns out that both the derivative and an integral, those tools are of a specific nature. These guys are limits. Now, you don't yet know what a limit is probably. That's what we're going to talk about. That's what this section is about. Limits and continuity. There's a mathematical object or idea that is called a limit. And using this idea, they have built these two tools, the derivative and the integral. And the derivative is a limit that solves the rate problem, while the integral is a limit that solves the area problem. So if you were to talk about the study of calculus in one word, it would be the study of limits, right? It's limits and their application. It's just that there are two different kinds of limits to solve two different kinds of problems. Okay? So that's kind of an overall grand scheme covering this course and the next course. Our focus is going to be here for the next month and a half. Okay? So that's where we're going. And because the derivative is a limit, we will start the conversation by talking about what is a limit. So now that's where we're going. So that's kind of a little bit of overview, just to sort of tell you where in the big picture this all fits in. Yeah, so the two important problems that calculus is meant to solve is the rate problem and the area problem. But it turns out on our journey to solve these two problems, we got a lot of collateral benefits out of it. There's a lot of other things we can figure out as a result of being able to figure out these problems. So let's actually start that journey with the limit. So let me tell you, there are like super esoteric, specific mathematical definitions for what a limit is, but we can get away with a little bit of a fuzzy definition. So here's a fuzzy definition of the limit. It's more than enough for what we'll be doing. Okay. So I'm going to tell you what a limit is. I'm going to tell you the notation that we can use to write it down. Then we're going to go through some examples with geometry to kind of get you to the idea, because it's heavily reliant on some geometric intuition. And then we can go extrapolate from that into calculations. How will we actually compute these guys? Okay, so let's start with a definition of a limit. So let f of x be a function. We say the limit as x approaches a of f of x is L, right? So this is a statement we can say. So I can make this statement. The limit as x approaches a of f of x is this number. And if we want to say that in a mathematical way, we would write down this notation. LIM, x gets close to a of f of x equals L, right? So I can say the limit as x approaches a of the function f of x is the number L, right? Now when I say that phrase, here's what it means. If, right, and here's where the fuzzy definition is coming in. As x gets close to a, the y values, in other words, the f of x values, get close to a unique number. Okay. So why this is fuzzy is because the word close, close can mean different things for different people. And so the idea of what does it mean to be close? I mean, this close, this close, this close, right? That can actually change from person to person. So there are definitions of the limit that actually make the word close precise, where everyone agrees that's close, there is no argument, it's a mathematical fact that this is close. For us, it's enough to have the intuitive notion of close. When the x values get close to something, we're looking at what the y values are doing. What does the y value get close to when x is getting close to something? Those are probably some phrases you should have in mind. So you should think, what are the y values doing? Or what is the y value getting close to? When x gets close to a. Right? A limit is merely an answer to that question. I do also want to emphasize, this is running out. This is another very important thing, and I should write it in red, it's a common misconception, but I'm not going to. There's an emphasis on close. Meaning, you do not want to take the interpretation that letting x get close to a means x is at a. We don't actually care about being in a certain position. We care about getting close to a certain position. And so a lot of students will get mixed up in that. If I tell you that the value of the function is this at this point, they'll think that's the limit. That's not the limit. We don't care about being at the position. We care about getting close to it. That's what makes the concept of a limit different from the concept of a y value itself. It's different from the y value. It's going to be a bunch of things leading up to that y value. You want to know what's leading up to a certain place. You don't want to actually be at that place, right? You really care about emphasis on getting close to some position, right? So, care about closeness, not about actually getting to a destination or being defined at a point. There will be a lot of times where there will be no y value. No y value will exist. Your function will be undefined, but we will be able to talk about a limit at that point. Okay? So that's very important that you know that. Right? You only care about getting close. Something crazy can be happening at that location, but you don't care. You care about getting close to that location. Okay? And that's the idea of a limit. When we realize when we enter our x value close to some value, look at what the y values are doing. How are they moving close? What value are they moving close to? They might not have to actually get there. So let's look at some examples. The first one, you probably won't get any nuance, but I'll sort of build on the nuance as we move along. So example. So what is the limit as x gets close to 1 of 2x plus 3? Right? So I can ask you that question. What is the limit as x gets close to 1 of that function? Okay. Now, here's the thought process you can go through. So 2x plus 3 looks like a straight line, positive slope, passing through y-intercept 3. You will notice the location 1 for the x. And what we're doing is, we're letting x get close to the value 1, right? So we're looking, okay, imagine our x values are getting closer and closer to that, right? Then that would mean the corresponding y values, right? So you're sort of looking at a trend of the x values getting closer and closer to this. But notice as the x moves here, the points, the y value will start inching up, right? So now, if you combine these and go on the curve, what you're talking about, you realize the points are moving in this direction. There's a move along that direction, okay? Now, there is a location that these guys are going towards, right? Now, I don't necessarily care about being at that location. I just want to know what's happening to the y values as we get close to that location, right? You can also examine it from the other side, right? So if we're getting close to 1 from this side, it means on the curve we're actually getting close to here, which means your y values are inching down. And so the question is, what is this value that the y values are getting close to? That's called the limit. What would this value be? Yeah?
5.
It would be 5, right? Now, I want you to be aware that technically we could actually get there, right? Because this is a straight line, it's defined everywhere. We could actually be at 5. I could just be like, at this point we're at 5, right? But it's very important that you think in along these lines when it's talking about a limit. You don't necessarily care about being at the point. You care about, well, if the x values are getting close to 1, the y values are getting close to 5. In fact, in this case, I can actually be at the location 1, and the y value will actually be the number 5. But the idea of getting close is what we care about. Let's look at another example. Now this example is different from the last one, obviously, because in this case, we cannot actually plug in the number x equals 1. Here we could have. We can actually be at that location. This is different though, we can't be at that location. For x to get close to 1, we would divide by 0. So there is no y value at that location. However, if I were to graph this, what would it look like? I think we've actually graphed something similar to this in class before. I might be mixing it up with another class. Yeah?
It'd be a parabola, right? But it would like have a hole at 1.
Well, it would be a parabola if we're dividing by the x. So the idea is here, you will notice that can't make x equals 1, but if we're close to 1, right? So I don't care about being at 1, but what if we're close to 1? So we're not quite 1. We're 1.000001, or we're 0.9999997, right? What's happening to this as we get close to 1? Now, if we're getting close to 1, so at 1, this is meaningless. It's gibberish. It does not exist. That makes no mathematical sense. However, as long as we're not at that point, this is just a fraction, right? and we can reduce it. I can look at x squared minus 1 over x minus 1. If I want to reduce that, what would it be? Right, so it's x minus 1 times x plus 1 over x minus 1. This cancels, so x plus 1. In other words, what we're saying here is that as long as we're not actually x equals 1, because x cannot be 1, but other than at x equals 1, we are behaving like this. We're behaving as if our function is x plus 1 itself, which means the sketch of this looks like the sketch of x plus 1. With the one difference is that at that one location, being at 1, we can't actually plug anything in there. So there is literally a hole in the graph at 1. When the x value is 1. Right? So now this is a situation in which we have no y value. There is no y value to speak of. However, I want to talk about the limit here. Now, so I don't care about being at that hole. However, if the x values start inching closer to 1, we're on the function like this. If I start doing that, we're on the function like this. And so now we're tracking these things across, right? We're paying attention to what's going on the y-axis, what's going on the y values. They are heading to what location? To 2. They will actually be getting closer to 2. Right? So in other words, I can say here, I can say that the limit as x approaches 1 of this function is 2, right? Now I want you to notice the y value does not exist there. There is no y value that outputs 2. The function itself never outputs that value. But the limit outputs a value. The limit is 2, right? Because the limit doesn't actually care about being at a location. It cares about what are the y values do as you get close to that location. So whether or not this is filled in is completely irrelevant for a limit, right? And that's very important for you to understand. Now, let us look at another situation. Say we're looking at that function. Now, of course, we cannot plug in x equals 0. But the limit doesn't care about being able to plug in. The limit cares about getting close to 0. So now we're going to talk about what would happen to on this function as we approach 0. What does the graph of this look like? This. And it looks like this. So here's the number 0 is what we care about. So now we're talking about getting close to 0. Let's get close to 0. So we're over here, getting close to 0. The corresponding points on the function will be, well, what's happening to the y values as we get close to 0 here?
It does not exist.
Well, here, these y values, you can't describe what behavior they're doing.
They're going to be empty.
So here we're like, x is getting close to 0, our y values are actually getting smaller and smaller. They're going up to negative infinity. However, you might notice something else. The other branch of this function actually behaves very differently. If we're getting close to 0 from this side, what's happening is that now we're on this function. And now you'd realize, well, as x gets close to 0, y is getting close to infinity here. And now here's where our definition from the limit is going to come in and kind of resolve this issue. Or kind of say the issue is not going to be resolved. We're going to actually look at something to talk about a concept like this. But in the definition, the limit was there needs to be some kind of certainty. There needs to be no ambiguity in your answer. When you say the limit is this number, it's a unique number that's happening. There should be no ambiguity here. And so what you realize is that depending on what side you're on, you can give two different answers to this question. As we get close to 0, what's happening to the y? Well, it's going to negative infinity. Well, no, positive infinity. No, negative infinity. No, positive infinity. Right? There's kind of a miscommunication here. There's a disconnect. Right? Now, whenever something like that happens to a function, we would say that the limit itself we would write DNE. It stands for does not exist. And it does not exist because there is no unique y value that we get close to when x gets close to 0. There are two different y values, right? And they're not even values, they're going off to infinity. But for us, infinity will be a meaningful answer. Because one of the points of a limit is to study the behavior of a function. Telling someone that the function is going off to infinity or negative infinity does describe some sort of behavior. So we're actually going to keep it as a valid answer. Right? So just being infinity in and of itself doesn't break anything. Let me actually give you a follow-up example to that same idea. If we instead looked at this guy, the limit as x approaches 0 of 1 over x squared, now we might notice that that graph looks like this. And we're approaching 0, so we're getting close to 0. So we're getting close, we're inching closer to 0. We can never actually get there because we divide by 0. But we're inching close, which means now we're on this graph, and you'll notice we're inching up. And so as x is close to 0, your y will get close to infinity. Conversely, on the other side, you'll notice that over here, as x approaches 0, y gets close to infinity. It turns out it's going to the same value in both directions. Same. So here we can make this statement. The limit as x approaches 0 of 1 over x squared, I can say that is infinity. And what I mean by that is when we get close to 0, the y values just keep getting bigger and bigger and bigger. Now that's different from this case because in this case, sometimes they get bigger and bigger, but sometimes they get smaller and smaller, and that disconnect is not good enough for a limit. Right? Now we do have a concept that can talk about what happens when two sides do a different thing, but I haven't introduced that yet. So for now, for us, we will say this limit does not exist, and this one is infinity. Let's look at another example, and you guys can tell me what the answer should be. We're going to define a function. Do I want to use this one? Yeah, let's use it. It's a piecewise function. We've had a bad history with these, but we're looking forward to the future. We can improve. Okay. Piecewise function they tell you a different thing that the function does in each region. So let's say you're given this function and we ask what is the limit as x approaches 1 of the function. Okay, what would you say here? So when x is close to 1, what does the y value do?
It's 1.
It's 1?
So when the x value is 1, the y is 1.
Well, sure, we can say, well, this tells us what happens when x is equal to 1. We can plug in 1 here, and we can get, that would give us 0, and that would give us 3. And so you can say, that would be 3. That would be the wrong answer. But I want you to appreciate why that's the wrong answer. If you say that, if you say, okay, if x equals 1, plug in 1 here, what are you finding? You're finding the y value. In other words, if someone answers 3, what they actually told me was what is f of 0. This is not the same as me asking this. These are two different questions, right? And this is what I meant, it's not about being at the value. I don't care when x is 1, what I plug in and I get. Completely irrelevant. It is not relevant at all when it comes to a limit. Limits care about getting close. I don't care at x equals 1 what is going on. It is an irrelevant question. Okay? That's why I really want to get to. So if you looked at this and thought, oh, well, here x can be 1, just put it in here. That's the wrong approach. You're finding a y value. You're not finding a limit. They're not the same. Okay. Let's go with a little bit of geometric approach again. Let's actually look at what's going on here. And sketching is often, again, another useful technique to solve problems like these, but you will also sometimes be given graphs, right? It's very common for them to actually give you a picture and ask you about a limit based on the picture, right? So you need to know how to read this on a graph as well. So obviously our function takes on two different behaviors around x equals 1. To the left of 1, it is 1, and to the right of 1, it behaves like a quadratic. So we can talk about, okay, here's where x equals 1. Y equals 1 would look like this, when it's just a horizontal line going all the way down. That's y equals 1. Okay? So on the left side of 1, I draw y equals 1. Now on the right side of 1, I should be drawing this quadratic. Now, this quadratic, we know what this looks like because we understand transformation of functions. Take x squared, shift it 1 unit to the right, shift it 3 units up. So I know what that graph looks like. So that would mean that guy would start at 3. And it would just look like a quadratic. Okay. So we have these two locations. Here's at 1, and here's at 3, and these are above 1. Now can you tell me what the limit is? Does not exist. Now it becomes obvious. Because it's not about plugging in. You see, the fact that this point is filled in, irrelevant. Right? If you care about where points are filled in, you care about y values. Caring about a limit is a very different consideration. Right? Now what you can realize is that, well, if we get close to 1, well, the y value is getting close to 1. But someone can say, no, hold on, wait. If we get close to 1, the y's are getting close to 3. There's a disconnect. There's a miscommunication. There is no unique y value. Sometimes you're getting close to 1, sometimes you're getting close to 3. So in this case, this limit would not exist. So that limit actually does not exist. So that's the very, it's nuanced, but it's a very important distinction, right? I know we've cared about y values our whole life, but right now we care about something else. We care about getting close. Not necessarily being at a location, but how is the function behaving when we get close to that location? Because sometimes a function can misbehave at a location, but we still want to be able to deal with it. And talk about its behavior, talk about its properties, make some descriptions. And ultimately, this is the kind of thinking that led to the calculus way of thinking, that led to us developing these tools. Now, understand the examples with does not exist. Might seem unsatisfying. So we can come up with new notions. Right? So here's the thing. So the real goal of a limit is to talk about the behavior of a function, not necessarily at a specific location, but what happens as you approach that location. Now, for someone to ask about the limit of a function like this, and they basically told you, I don't know what the hell is going on, it's not really satisfactory because this is not a very complicated function to understand. I can look, I can see what's going on. You should be able to describe to me something. You can't tell me nothing, seriously, right? It's not very difficult to see what's going on with this function. So sometimes looking at a limit as we've defined it is just not good enough because there are some very simple situations that it just can't handle. And so what we do is we develop these new notions of one-sided limits. So now there's a concept of a one-sided limit. And this is about when your x is inching close to a value from one side at a time. So I can define, and sort of tell you what they are just by the notation. So here's how we might affect this notation. We can put a little plus sign here in the power as a superscript of f of x. And we call this the limit as x gets close to a from the right. Okay. So that little plus means we're a little bit more than a, so we're on the right side of a, and we're getting close to the function from the right side. And we can similarly talk about that notation, putting a little minus sign at the top to be the limit as x approaches a so we can talk about this. So, for example, on the previous example, right, so this guy, let's say instead of asking you what the limit is, I ask you about these specific limits. Would you have answers now?
Yes.
What would this one be?
3.
3. This one?
1.
1. Now we can have specific answers. Now overall, the limit does not exist because there was no y value that we could say we're getting close to. But if you look at one side at a time, we can describe what's happening to the function. On the right side, the y values are getting close to 3. On the left side, they're getting close to 1. So overall, there's no one y value that we're all getting close to. But I can talk about the behavior of the function on either side, right? So when we want to talk about that, we say we're taking one-sided limits. You can take a right-hand limit or a left-hand limit. And it's important that when you're looking at the right-hand limit, you only care about approaching from the right side. So you're pretty much tracking what the function is doing along the right side, and you ignore the left side. So looking here. Whereas when you're talking about this, this guy is coming from the left side. So you're pretty much tracking what are my y values doing on this side, and you ignore the other side. So that's the notion of a one-sided limit. We can also talk about we can redefine what a limit is in terms of these two guys. And so this will actually give us some sort of basis for determining a lot of problems. We can say the limit as x approaches a of f of x only exists if both one-sided limits exist. And they are equal. Right? So notice that in all the cases where we saw the limit actually exist and we could write something down, like in the 2x plus 3 case, or the y equals x squared minus 1 over x minus 1 case, or even the y equals 1 over x squared case. How we knew these guys had an answer and we could write them down is you could look at, I think we were always approaching 1 here. Here we're approaching 0. Is we could say that the limit as we approach 1 from the left was of f of x. This is 5, because if we approach here, that gives us 5. And the limit as x approaches 1 from the right of f was also 5. If we do this from here, that's also 5. So these being equal, this means that the limit is 5. Right, like the overall limit. Same thing from here. If the limit as x approaches 1 from the left of f, it was 2. The limit as x approaches 1 from the right of f was 2. So we could say that the limit is 2. Similarly here, I could say that the limit as x is approaching 0 from the right of f, from on the right side, the y values keep getting bigger and bigger and bigger. I would describe that by saying infinity. Now if I look on the left side of 0, I would also describe the behavior as infinity. Okay. So because these two were agreeing, we can say the limit is infinity. Now 1 over x didn't work because the right side gave you positive infinity while the left side gave you negative infinity. And so these two guys were not equal, and so we could say the overall limit would not exist. So that's the idea of a limit. We'll pick up with that next time. So that's the idea, to really start thinking about it. Next time we'll go into a lot of computations. We'll talk about continuity. Yeah, so next time should be fun. We should be able to get to the derivative by next time. It's gonna be pretty interesting how that guy comes out of ideas like this. So we'll stop there. Yes.
So all the questions for the homework, it's about the homework. It's due today, right?
Which one?
Like here in section 1.4, it was.
I'll check.
Yeah, it's just a lot of questions.
I don't remember.
I just said this to my homework for 11:59 p.m.